Hello and welcome back to PC Retro Programmer. In the past couple of videos we've been looking at assembly optimization for the 8088 CPU. We've already been through all of the main optimizations that you'd want to apply to get generally good performance. And in today's video I'm going to look at some more specific ones that only apply in certain circumstances. The reason that I'm making this video is that when I got back into assembly language programming a few years back, I was disappointed to find that something like this didn't already exist. The best I could find was Michael Abrash's book, The Zen of Assembly Language, but it's a pretty big book and it's nice to have a condensed resource somewhere, and there may also be some stuff here that's not there. And I'm sure that I'm going to forget some things. If you can come up with optimizations that I've missed, it might be useful for other viewers to put them in the comments below on this video, and who knows, perhaps they'll make it into a later video on the channel. But it's important to realize that many of the optimizations for these early CPUs don't apply for the later CPUs. From 8386 onwards, things are a little bit different, even though they're technically backwards compatible. And so this video shouldn't be taken as a general guide to x86 optimization, for example. Now, before we get on to the specific optimizations, there's one more general one which I didn't include on the list or in the previous videos because it's really quite abstract and difficult to summarize. It really requires a video in its own right with explicit examples, and we will get back to that later, especially when we do our line drawing optimization. But I do want to mention it briefly here for completeness. The idea is to take state or values that you're explicitly keeping track of in your program, say in a register or a memory location, and to make them implicit depending on where you're up to in your code. So they're never actually explicitly stored anywhere. You just know what value there should be at any given point in the program. So effectively what you're doing is transferring information from some explicit place to essentially the instruction pointer. Now, I know that sounds a little bit wild, but the way it would work normally is you'd find some variable that can only take a limited number of values in your program, let's say 0 through 3, and then you duplicate your program that many times, once for each of those values, and then optimize each of the cases individually. And this can give you a speed up because something that was previously a variable might now be a constant in any given case and could just be encoded using an immediate value, say, freeing up a register. Or maybe you had some function that you were computing whose output only depended on that value or state, and now in any given case you know what the value of that function should be. It's now a constant in that case, and so now you don't need to actually compute the function. You just basically do it by hand as you're writing the program for each individual case beforehand. So this is an important optimization, but as I said, it's a bit wild to describe and we'll have to come back to it in a later video. Now, getting back to our list, we've already dealt with everything up to and including lookup tables, so let's move on to signed arithmetic. When I first started assembly language programming, I noticed that imul and idiv, which deal with signed values, are slower than their unsigned counterparts mul and div. And so I reasoned that you should always use unsigned values wherever possible. Now, this is sometimes true, especially where it's natural, but sometimes it's faster to let the CPU deal with the signs than for you to do it explicitly yourself. And we did this, for example, in our Mandelbrot set program, where we got a faster result by letting the CPU do the signs. So obviously there's imul and idiv, but there's a whole range of instructions designed for signed arithmetic. For example, to divide a signed value by a power of 2, you want to shift it right, but you want to preserve the sign. And this is what the SAR instruction does, the shift arithmetic right, as opposed to SHR, which is the unsigned variant, which doesn't preserve the sign. Or if you're comparing two values using the CMP instruction, the CPU doesn't care whether they're signed or unsigned. It sets the flags for both cases, and the way you interpret this comparison depends on the subsequent conditional jumps that you use. If you want to do signed comparison, you use the signed conditional jumps, JL and JG. There's also JLE and JGE. This is jump if less than, jump if greater than, jump if less than or equal to, and so on. These are the signed versions, And there are unsigned versions, JB for jump if below, JA for jump if above, and so on. And then sometimes you need to convert values from an 8-bit signed value to a 16-bit, or expand a 16-bit one out to a 32-bit one, and this is what CBW and CWD are for respectively. So if you learn how to use all of these, then very often you can get a faster result by letting the CPU do the signs. The next thing on the list is to use the flags to store information. And the most common occurrence of this is if you have values in your program that are a little too large to store in a 16-bit register, but would fit if you had 17 bits. So you use the carry flag as an additional bit of information. Of course, you have to be careful that you don't then use instructions that stomp on the carry flag, but there are even instructions on the machine which support this approach. For example, the shift instructions will shift out a bit into the carry flag, and there are also the rotate through carry instructions. So this can often give a speed up where you might otherwise need to use 32 bits of registers instead of 16. The next thing on the list is to use the inc and dec instructions to add and subtract 1 instead of using an add or sub instruction. Now this is only true on these very early CPUs. On much later CPUs, especially Intel ones, the inc and dec instructions can actually be slower. But here, there are only 2 cycles of execution time. Obviously on an 8088 it's going to be a minimum of 4 anyway because of the prefetch, but that's still faster than using an add or sub instruction. And moreover, inc and dec don't modify the carry flag. And the reason they did this is because they're usually used for incrementing and decrementing loop counters in a way that doesn't mess up the carry flag, which might have been set because of some arithmetic that you're currently doing. So these instructions can be very useful as opposed to just add and sub. Now moving down our list, the next one is to save and restore the flags using LAHF and SAHF. Now obviously there's pushF and popF for saving the flags on the stack, but this is very slow, and in comparison these instructions will just store the flags in the AH register, assuming it's available of course, and this will be much faster. Now they're usually used when you're doing some kind of arithmetic comparison, and you don't need to use the flags that are set as a result immediately. You want to put some other instructions in between. So you save the flags for later use and just restore them when you need them. Now, something to bear in mind with these instructions is they're not available on some later CPUs. Of course, that's not a problem for us. They're certainly always available on these very early CPUs. The next thing on the list is to keep the accumulator free if possible. If not the 16-bit accumulator AX, then at least the 8-bit accumulator AL. And the reason for this is twofold. The first reason is just generic. If you don't leave some register free, you won't have anything left to do temporary computations into. It's very tempting to just allocate all the registers on the CPU for something, but then you'll find yourself continuously moving data all about, trying to free up some space in order to do your computations. The second reason is more to do with the accumulator itself, and this has to do with the history of the Intel CPUs. Before the 8086 and 8088, CPUs often had instructions that only dealt with the accumulator, and this kind of carried over into the 8086 and 8088 in that the accumulator is still special somehow. As we've seen before, there are instructions that are faster if you use the accumulator. And because you're typically going to have a lot more temporary computations in your program than other computations, you want to leave the fastest register for this. The next advice on the list is sometimes true and sometimes not true. It is to use registers where possible instead of immediate values. Now, the reasoning here is that doing a computation with a value that's already in a register is going to be faster than first loading it from memory as part of your program code as an immediate value, which is going to take prefetch time. But obviously it depends on the context. It might be that you made that constant an immediate value precisely because you wanted to free up a register for something else more important. So this advice really only applies if you have spare registers, say when you're doing a loop or something. If there's an immediate value in that loop, preloaded into the register before the loop starts, and then it's just always instantly available instead of having to be prefetched as part of the program code every time the loop iterates. The next thing on our list is again something that really needs examples to make it clear, and it's actually something that's not always possible to do for reasons that aren't obvious. Very often you have a program that has a lot of cases that need to be dealt with, and each of them has a loop to deal with it. And once that loop finishes, there'll be some kind of jump or conditional jump instruction to jump off to the next case that needs to be dealt with. And one optimization principle is that you can sometimes rearrange these blocks of code so that when one loop finishes, the next piece of code happens to be the next case that needs to be dealt with, and so no jump instruction is needed. The reason that it can't always be done is that you may have other limitations on where you can put your blocks of code. For example, you want your jumps to be short jumps instead of long jumps, for example. So we'll see examples of this when we come to do our line drawing code. Now, the next thing we've already mentioned, and so I don't need to say much about it, that is to unroll loops, which is sometimes called speed coding in the demo scene. But the reason I mention it again is because sometimes it's not a good idea. For example, it can cause short jumps to become long jumps. It might mean that you end up having to allocate space elsewhere in another segment, meaning you need far pointers in your program all of a sudden. It also bloats your binary and so on. There are lots of reasons why it can be bad. Obviously though, in the case where you want every cycle that you can get out of the machine, it can be an important technique. The next thing on the list is to think carefully about whether memory variables and immediate values need to be 16 bits or whether you can get away with an 8-bit value. And this is important because on the 8088 it's going to take a lot longer to load a 16-bit value from memory than an 8-bit one. Now for registers it's not usually an issue. The 8-bit operations and 16-bit operations are usually the same speed, apart from, for example, multiplication and division. But for memory it really matters. Now there are some exceptions in the case of registers. We mentioned previously some instructions that are actually optimized for 16-bit registers, but apart from those it's usually not an issue there. Now one other consideration has to do with immediate values. Normally this is not important because the assembler takes care of everything for you, but if you're writing self-modifying code, it's worth knowing that some of the assembly language instructions, in particular some of the arithmetic ones, actually have an option to use an 8-bit value with a 16-bit register. And what they do is they sign extend that 8-bit value automatically out to 16 bits before combining it with the register. And this saves you a byte of machine code since you can use an 8-bit immediate even though it's a 16-bit operation. So this is really worth knowing about, as I said, if you have to write any self-modifying code. The next advice on the list is to play to the strengths of the CPU, and obviously the 8086 and 8088 are 16 bits internally, which is certainly a strength. It's a lot easier to do a 16-bit operation than a whole bunch of 8-bit operations instead. But that can also go the other way as well. For example, sometimes it's faster to think of the CPU as 8 bits with 8-bit registers and operations, accessing 8-bit memory locations and 8-bit immediate values, as we just said. So although that can go either way, there are two ways in which these CPUs are quite powerful. One is that they can address up to 1 megabyte of memory using segments, which is a feature that's usually not available on 8-bit CPUs. They're typically limited to 64 kilobytes of memory. And there are also very powerful addressing modes, which are typically not available on other CPUs. You can combine a bunch of registers and a constant in order to get an address to look something up in memory. So it really does pay to think about how you can take advantage of all this extra memory, for example, lookup tables, and these addressing modes in order to get the most out of these CPUs. We're nearly through our list, and we'll finish with some items which are often more trouble than they're worth. But first a word on the 8086 CPU. This has a 16-bit data bus, unlike the 8-bit data bus of the 8088. And what this means is it can load 16 bits at a time instead of just 8. But this is only fast if it's an aligned access. And what that means is that the data has to start on an address that's even. If the address is odd, it'll have to do 2 accesses instead of 1 to get the 16 bits, and this will be slower. And this is a problem for your program code because every time you do a jump or a loop to a label, then the prefetch queue of the CPU is cleared, and that means that it's actually got to load the instruction at the location you're jumping to. And if that's an unaligned access, that's going to cause a slowdown every time that jump is taken. So the compromise is to pad the code out by adding an extra no-op instruction, which is just a single byte, before that label, and this will push the label out to an even address. Now on the 8088, that's just going to slow things down because you'll have an extra no-op in your program. But on the 8086, this is going to make a big difference because every time you jump to that label, you'll be saving time from the load on the aligned access. Now you have to be pretty careful about this. The assembler has some align directives to allow this to be done quite easily, but sometimes I've noticed TASM gets it wrong and puts the wrong number of no-ops in. So it's always worth disassembling your program, say with debug, and just making sure that it did the right thing. The next thing on our list is self-modifying code, and this is something that can save both space and on occasion also time. But it's not for the faint of heart. It's hard to get right and it's a bit hacky. The idea is that in your program code you have some locations that essentially start out empty, and before you get there at runtime you have some other part of your program write into those locations the machine code bytes that are missing. So in other words, you have some part of your code modify some other part of your code at runtime before it's actually executed. Now this can save space. For example, if you have a function which has a number of cases to deal with which are almost identical, maybe they just differ by a few machine code bytes each, then you can replace all of those cases with just a single case plus some self-modification. It would just write into the missing bytes the machine code for the specific case that you want to run just before it's run. Now you have to be very careful about this. There is no default code that's going to run if you don't modify it. So basically every time that code is run, it has to be modified for the case that you want to actually execute. Now there are other issues with it as well. Obviously the self-modification is slow. You're writing into memory locations after all when you're putting those machine code bytes in, and so in general it's a slowdown. However, by making the code smaller, you can sometimes also get speed ups. For example, long jumps might become short jumps, or maybe you can fit everything in 64K now and don't have to use far pointers in your program. Or you can combine self-modification with a bunch of other tricks, for example loop unrolling, and get other speed ups that way. So it can be an important technique, but even for an expert it can be quite difficult to get right. After all, you're essentially doing the job of an assembler. You're having to write machine code instead of assembly language. You have to make sure you allocate the right number of bytes for the machine code, and you have to make sure you write the correct bytes in, which can be quite hard because it's not something we're used to dealing with. The final two things on our list are things that you want to do really quite rarely. The first of these is to use the stack pointer as an extra register. You remember that there are 8 registers on the machine that are general purpose, but normally SP can't be used because it's in use for the stack. But if you're not using the stack and you turn interrupts off so that they're not using the stack, then you are free to actually use SP as a general purpose register. Of course, you have to save its value somewhere, obviously not on the stack, and restore it again later so that it goes back to being a stack pointer when you're done. But other than that restriction, there's no problem with using it as an additional register. The main issue is that there aren't very many times when you would want to do this. Probably if you are trying to do it, it's because you want extra performance, and that means you're probably writing a demo or a game. And in a demo, you've probably got music playing, which uses interrupts. And in a game, you've probably got a lot of keyboard action, which uses interrupts. And so you can't really turn them off, and that makes this technique invalid. So that doesn't leave very many cases where this is actually a useful technique. The final thing on our list is also something that is generally not encouraged, but it can speed up the system by a few percent, which might make the difference between something working and not working. The idea is to slow down the dynamic RAM refresh. It turns out that the memory on these machines requires periodic refreshing. There's a timer set aside for this, and every time it counts down to 0, which happens a little bit more often than 60,000 times a second, it causes the DMA controller to refresh part of the memory on the system. Now, the DMA controller will tie up the bus when this happens, and as we know, the CPU requires the bus almost all the time. So this does cause the system to slow down slightly. So if we slow down that DRAM refresh, the rate that it happens, then we get a few of those cycles back. But we are technically putting the DRAM out of spec when we do this. It's not a problem in practice. Most DRAM chips can go a long way out of spec before they start throwing errors. But technically you're doing something a little bit risky, and for that reason the whole technique is considered a little bit hackish. There are times when it's actually necessary for other reasons, but those are quite technical, and I think they're best left for another video on the channel.